Okay, guys, so we had a bit of a technical issue. It actually kind of works out. That way, um, I might just do chapter 8, one big chapter 8 here, and just be done with it. And that would be kind of nice. Well, it won't be done. I mean, but we'll go through it in one shot, and that might be beneficial. So we'll see. Let's see. I need to share screen. That's what I got to do. Share my screen, and then this is going to be. I'm going to be using the computer here in tablet mode, so no need to be looking at my ceiling. Turn off my camera. Flip my computer over. Okay. So cool. This should be fine. Let's move a few things around that I like. Okay. Nice. Okay. So cool. Chapter. I am screen sharing, and I am recording. Okay. So this should be good. I really don't want to spend the next 2 hours having to redo all this. That would not make me happy. So we're just going to start over with chapter 8. Chapter 8, transducers. And the way a transducer works, we already discussed that transducer could be anything. It's your eyes, your ears, your speakers, microphones. They're all transducers in a sense. They take one form of energy and change it into another form of energy. So we have transmission and reception. And so I kind of have a little bit of a, let's see, I don't want to see you. Don't want to see you. No, I don't want to see you. All right, there we go. Just got to use something else, I guess. Okay, so transmission. So that represents the electrons. In other words, electricity produced in the machine produce a transmission. Transmission of sound, actually. And so that makes sound come out. Let me get rid of those. And then reception. Cheater makes me write nicer. Also change my pen. Reception of sound. So sound coming back pushes on the piezoelectric material and creates electricity. So E minus is just electron, right? So during transmission, the machine produces an electric charge, a current, goes through the wire, hits the piezoelectric material. That piezoelectric material essentially rings, just like a bell will ring, and sound is produced. And then sounds, of course, they have echoes. The sound beam has echoes, and so I say sound down here. What I also really mean is the echo. But those sound waves, physically, they physically bump into the piezoelectric material. And the strange thing about piezoelectric materials is that they produce electricity when they are pressed upon. I have the weirdest, no, we don't have them anymore, but I had these fake wicker chairs, a kind of plastic wicker. And whenever I would stand up and I'd push my palms down on the arms of the chair, I'd get electrocuted every time. And I'm not sure, but I think my chair was piezoelectric. I pushed on the chair, it created an electric charge, which means if I added electricity to the chair, perhaps it would produce a sound. I don't know. Haven't tried it. Don't think I ever will. But so piezoelectric effect, reverse piezoelectric effect, it's basically the same thing. We'll talk more about this. Well, let's talk a little bit more about what these are made of. So generally, piezoelectric materials in ultrasound are made from PZT. That stands for lead zirconate titanate. Titanate, yes. Now, you might be wondering why P lead is PB, yes. And the periodic table lead goes by another language, probably Latin, and so PB is the symbol for lead. So that's why it's PZT and not LZT. That's the most common. That's probably the one they'll ask you about on the SPI, the SPI, as some people call it. Where do we have other? Okay, so far I just have, there's usually a question, perhaps in my other physics book, they have some other formulations that also create piezoelectric materials, but I think this book only has this one. So PZT is in a part of the transducer called the element. So the piezoelectric material is in the element. We've drawn here is a simplified transducer. This is a one element transducer. Actually, the transducers you use have many elements, but this one's a one element just for simplicity's sake. The green is our lead zirconate titanate. That is, let's see, let's just do that. PZT, also called the element, also called crystal, ceramic. It is a ceramic, that's why I call it ceramic sometimes. It's also crystalline, that's why they call it crystal. Element, because it's elementary, dear Watson, and PZT because it's the lead zirconate titanate. So all of those really mean the same thing. Okay, next page, basic transducer construction. So I've already mentioned one part of the transducer, and that's the element itself. This is the part that electricity comes down, hits the element vibrates and creates a sound wave. Echoes come back, those sounds come back. They in turn push upon, their energy hits the element, and that creates an electrical charge that goes back to the machine. And that's all you need to do. No, unfortunately, that's not all you need to know. Let's go in. So, okay, so some of these are just stupid. It's like you couldn't figure out that the outside is the case. All right, plastic case. That's, I don't even think it's worth mentioning, but oh well. Electric shield. These are actually different colors, but you barely see it. So let me zoom in just a little bit more here. Electric shield is right here, yowzas. Shield. So when crazy people and paranoid schizophrenics put tinfoil on their heads so that the government stops listening to their thoughts, they are putting on an electric shield. They're basically creating what's called a Faraday cage where electricity, like air and electricity, is like literally not so much electric. You don't want any kind of crosstalk with the outside world, and that does sometimes happen. You'll go into a room and some of the machines will just cause havoc with your machine. This next layer in here is a acoustic insulator. I probably could have made that a little thicker. And so you literally, you don't want sound waves coming out, or you don't want sound waves coming in, or any kind of physical interference from the outside world. You don't want that in there. Or we've already mentioned the active element, the wire. Okay, so this is a one-wire system. Normally, trust me, there's more than one wire going in to a transducer, but we'll just do the one wire for now. There's another term I want to use. Well, I'll use it in a second. All right. Matching layer and backing material. So I need to move this down a little bit. Now, these are going to take a little more explanation. Here is our, and I did the colors more or less the same as the colors on page 114, if you're wondering why I chose these colors. Matching layer. That's basically when you look at your transducer head on, it's kind of a gray black material, rubbery material. That is actually the matching layer. That's the part that goes against the skin, or more precisely against the gel, which goes against the skin. We already mentioned that's our element in green. And then this guy, this is really important too. This is our backing material. Also called damping. I used to, for the fun of it, I used to call it the damn damping material, and one of my students actually thought it was called damn dampening. Called the damping element. Damping. How about this? Material or damping element. And it does what it sounds. It dampens the sound. Okay, so as we move on, page 116 in the book, we're going to get into a little more detail about what some of these layers do. The matching layer is a rather important layer, so we'll talk about that. So we've talked about impedance. Z1, Z2. We've talked about the fact that if a sound beam comes down and there is a very large difference in the impedance between Z1 and Z2, if it's very large, then virtually 100% of the sound is reflected. And imaging at that point is useless because we've completely lost our beam. Our beam has completely been reflected. Attenuation is basically 100%. Not a good situation. Now, sound is produced in the element, right? Where the element produces sound, but it's basically produced in the element. Do you think the density and speed of sound in a ceramic is similar in as the density and the speed of sound in soft tissue? Probably not, right? If I were to call this, you can't see that, can you? Let's see. Purple. If I were to call this Z1 and the tissue Z2, there is a huge impedance difference. So theoretically, this should occur. All the sound should be reflected back right at the skin layer, and no imaging would be allowed. Give you some of this. Okay. That's what the matching layer is for. The impedance of the piezoelectric material is about 20 times greater than soft tissue. The matching layer, and here's a little trick or a little something that the book doesn't mention, it's okay. There's oftentimes multiple matching layers, and each matching layer is like, well, it's kind of like, let's see, if we have a house here, and then we have a floor down below, and so here you are. You don't want to make that jump, you'll break your legs. In the world of ultrasound, you just won't even go. But if we step down, we can make it. So that stairways from the upper level down to the lower level is basically like the matching layer. It's a step down process. And so multiple matching layers, or even if it is only one matching layer, it isn't, the matching layer is a intermediate impedance, between the element or the crystal or the ceramic, whatever you want to call it, and soft tissue. And actually, we have another intermediate step. Even beyond the matching layer, I will tell you, let's see, let's use something fun here. I think that's okay. Yeah, sure, I guess. Let's say we'll make this yellow. Well, I don't look right, but in any case, it's okay. The gel we put down, also called a coupling gel, it does two things. One, it is formulated to be the correct impedance to facilitate sound going from the transducer, matching layer, gel, skin, body. So its impedance is carefully calculated. It's called a coupling gel because it's making a coupling, almost like a solid connection between the transducer and the skin. Because, zoom in a little, because if we have even the tiniest air bubbles, those tiny, tiny air bubbles, or even just not even a bubble, but just like a film of air. Super thin, molecules thin. That's still enough for the sound to hit that air and bounce back. And no image is possible if that occurs. That's what our gel does. It's not for sliding around or any other extracurricular activity. It's just for removing that thin layer of air, because that's all it takes is a super thin layer of air to totally ruin our image. So let me read here. We call it difference. Yeah, impedance is about 20. Gel further increases. This is why gel's got a couple. I didn't even read that, guys, and I got that whole page right. Oh, and thickness counts. Okay. Let me zoom in, and hopefully I can write right in here. The thickness of the matching layer or layers, 1/4 lambda. All right, just remember that it's 1/4 lambda. Oh, and they give the active element as well, and that is 1/2 lambda. And I'll tell you the 1/4 lambda is a little bit of a mystery, but the 1/2 lambda, I figured that out why it's 1/2, and we'll talk about that shortly. Okay, the backing material. Oops. Backing material or damping material, damping element, plays an essential role in optimizing the pulses created by imaging transducers. With backing material, short pulses are produced. So I'm going to pause this just for a second and grab a piece of crystal that we drink out of. Hold on. Okay, I had to go through a few low quality items in my house before I found something that a little higher quality. Okay, so what happens when you ring a bell, right? You ring a bell and sounds, hopefully you guys can hear this okay. So what that sound is vibrations of, well, let's just pretend it's the element. It's vibrations of the element. What do you think the pulse duration or the spatial pulse length is on something that sounds like that? Can you see where I would say that that is almost a continuous wave transducer? It produces a constant ring of sound, and so that ring. Let's draw that out here. And so I have a glass. It's going to be filled with bourbon later. Oops. Oh well. And I'm hitting it. And it's vibrating. The walls are vibrating and creating a sound. Well, actually, let's draw it. Let's draw it like this. It's creating a sound. Son of a bee. Try that again. Okay. This is essentially a continuous wave transducer. This is no good for imaging. This is, it's not even measuring an ant with a yardstick. It's more like measuring an ant with a, I don't know, a football field. It's just kind of just keeps going on and on. So what we want is this, right? That's what we want. That's what we have to have in order to make imaging. So all I have to do, and you can't see me, and I'm not going to change everything up just for this purpose here, but we got to go from that to that. Same crystal. What you're hearing there is my hand wrapped all the way around the glass, acting as a backing material or damping material. That is how we get a 3 or 2 or 4, whatever cycle pulse, all right? That's really important, very important. So that backing material is essential. Oh, guess what? Guess what continuous wave transducers don't have? Backing material. So that's one big difference between an imaging transducer like we have and a continuous wave transducer. This whole level here, it does not exist in a continuous wave, because in a continuous wave you want that constant sound. Okay, so well, there's some things. Let me just high degree of sound. So the characteristics of a damping material, high degree of sound absorption. Well, yeah, that's the whole point. You also, by the way, you also have, you don't want, if this piezoelectric element, this green element is ringing, you know, it's not only going to ring in that direction, it's going to, you know, it's going to want to put sound in both directions. And so you don't want sound going back into the transducer, because then it bounces around, it'll make a mess of things. So what the construction of a continuous wave, they have damping material or acoustic inhibitors, but they don't inhibit the ringing of the bell or the ringing of the element. Okay. So high degree of sound absorption, an acoustic impedance similar to the PZT. Well, why? Because you actually want the sound not necessarily to bounce back and forth here. You do want the sound to go in here. You just want it to be completely absorbed. Impedance of damping element similar, so the sound wave created moves into the damping element away from absorbed. Yeah. So there are consequences that are not necessarily good. Everything is a balance in ultrasound. So the backing material let's zoom in a little bit so I could write a little more clearly. Decreased sensitivity. When that backing material, the reason for it is on transmission, you want a short wave pulse. You want a short pulse. That's the good part. The bad part is on reception, as you can imagine, if you try to ring the bell again using sound energy, it's going to be muffled because of the backing material. So unfortunately, it decreases our sensitivity, which tells us that continuous wave transducers have better sensitivity. It creates a wide bandwidth, and we talk about that on the next page. Yes, so I'll hold off on bandwidth. Well, I'll hold off on the next one too, because that goes with it. In low Q, or actually quality, and that's oftentimes just referred to as Q factor. So decreased sensitivity, bad. Wide bandwidth, actually not bad. Low quality, well, these two are, they go together. Okay. So bandwidth, let's talk about that. I've got a little picture here, of course. So what I have here, these are bell curves. I assume you guys know what a bell curve means, but basically if you have, you usually have some kind of amount down here. This could be IQ. So your IQ points, and 100s in the middle, 90, 80, whatever. That could be IQ. It's a distribution pattern, basically. Distribution pattern. When we have a continuous wave transducer, oh, I almost dropped my crystal, and it produces a sound such as that. If we could see that sound on, like let's say on an oscilloscope, it would be pretty much one frequency. Whatever frequency that is, we would see that. And so most of this mostly one frequency. And so that's, one note. This is what we see with continuous wave transducers. They have a pretty sound. So let me talk about quality factor in the same breath here. It's a high quality sound. Whoops. So when we talk about high Q versus low Q, it's literally the quality of the sound. This, it's pleasant to the ears. It actually has high quality. It's mostly one frequency. They have maybe some little extra frequencies coming in at the bottom here. Extra frequencies, but for the most part, it's one. Okay, that's continuous wave transducers. Our transducers have a wide band. Oh, and let me just finish one thing. Narrow bandwidth. Okay, now we're talking about our transducers. Pulsed, I'll add imaging transducers. Many frequencies. So even though we say we're imaging at, let's say, 5 megahertz, well, this might be 5, and of course now we're going to be megahertz scale, 5, 4, 1. Oh, well that doesn't really, that doesn't quite go. there. All right, 5, 6, 7. Okay. So our scale at the bottom is megahertz. 5 might be the fundamental frequency. So we'll put F0, or the operating frequency. But there are other frequencies are buried in there. And so, well, let's hear what that sounds like. That's low quality. So let's just low Q, wide. And by the way, when you hear wide bandwidth and with your electrical, your electronics, this is the same thing. It's a bandwidth that they're able to use. So at first, this wide bandwidth was not used. The engineers kind of figured it out pretty quickly, though. It says, hey, you know, we have all this ugliness over here, and it's an ugly sound. It's a low quality, ugly sound, but let's take advantage of that. And so let's take the 4 megahertz and the 6 megahertz, and let's use that to our advantage. And so this is where multi-frequency transducers come from, these wide bandwidths. You can't do that, by the way, with a continuous wave transducer because it has a narrow bandwidth. It's not really a multi-element. It's not a multi-element. It's not a multi-frequency transducer, although there are other ways of changing the frequency on a continuous wave. But we'll hit that later. Okay, so let me just read through back material. Wide, broad. Oh, it's also called, let's just add another term. Broadband. You guys have all heard of that. That's electricity broadband, but sound can come in broadband as well. Quality factor, gosh. Q is equal to F0. We don't really need to know this. That's on page 119. F0 is, FO really is operating frequency divided by the bandwidth, gives us our quality factor. But literally, it's quality of sound. Ugly sound is what we use. More about piezoelectric. How is the piezoelectric material created? Yes, well, I'm going to use this little corner over here because it's not much to talk about. But I could add a little bit that the book is not showing us here. So let's say we have this material. In fact, we could mix together lead zirconate titanate, PZT, and we'll make a little rectangle of it. We mix it together, dry it, whatever. It is not yet piezoelectric. It's simply some ceramic sitting there. So it's not so much that the chemical compounds create the piezoelectricity. What needs to happen is that we put that into an oven. Let's do a little, I'll draw, oh, this would be nice. So, draw a little oven. Of course, every oven's got to have little dials on it. And we have a little window to the oven where we can see our piezoelectric material getting cooked. And why does it always choose the wrong color, green? Piezoelectric material is getting cooked in that oven to a certain temperature. It's called the Curie point temperature after Madame Curie. So it has to Curie point temperature. I think it's around 1200 degrees. I had it written somewhere, but unfortunately not here. It's around 1200 degrees is the Curie point temperature. But we're not done. We've heated the material. We've heated this piezoelectric material. Now we need to add a current through it. Electric field. Electric field, electric current, same difference. So let's see how we're going to display that. That's going to be the electric field is going to go right through that. And what happens on a more of a microscopic level is, well, you know what, I'm not going to draw it out because I'll draw it incorrectly. But it's actually kind of interesting. It arranges the molecules in such a way that if you push on them in one direction, the electrons are kind of get pushed out. And if you add electrons to the system, it deforms again. And so when we think about these things, here's my now newly minted piezoelectric material. When when electricity is applied, it vibrates, and so it gets it gets a little bit wider, like the wall. This wall has increased and increased there, so it's actually gotten wider. And then it'll also get thinner. So that's a little bit unclear. Let me just draw it like this. We'll start off with our unchanged, actually I'll draw another one here. But now I need to okay. So here's our element. Just resting. It's not listening to sound, nor is it getting hit with electricity. When it gets hit with electricity, it will expand ever so slightly. Doesn't take much. When I hit my crystal, I don't see it vibrating, but it is. If we had slow motion and real close up, we could actually see it vibrating. And likewise, when this element, let's just go ahead and use this guy. When sound comes from below, let's say, comes back and runs into this guy, it's going to ever so slightly deform. I'll leave this one straight because it's deforming that side. Ever so slightly deform that element, and electrons are pushed away. And that is our echo. So our echo comes from here. This information is going to go to the computer for processing, and then eventually be displayed on the screen. So anyways, I kind of went a little bit off topic there. Curie point temperature, I think is 1200 degrees. And once it reaches that temperature, an electric field is put through it, which arranges the molecules in a certain way to create piezoelectric material. Oh yes, we do not put transducers into very hot environments, because if you approach, now I don't think it's very easy to reach 1200 degrees unless it's an autoclave, but if you put a transducer in an autoclave, it will depolarize, and you've ruined that transducer permanently. So, not to mention, I think most of it would melt at 1200 degrees, but so a lot of people they don't even want to use hot water on it because they think they're going to reach the Curie point. I doubt they will, but lots of people are depolarization. So this one is polarized. Depolarization would occur if you reach the Curie point. Again, they have a one quick thing: sterilization, disinfection. Sterilization is destruction of all microorganisms by exposure to extreme heat, chemical agents, or radiation. Disinfection is good, but not 100% effective. It is the application of a chemical agent to reduce or eliminate infectious organisms. So disinfection attempts to significantly reduce the microbial load. Anyway, I'm going to keep moving on. Transducer frequency. What determines the frequency of sound? Oh, I love this one because I figured it out. And this is going to be a long. Continuous wave transducers. Ultrasound system produces a continuous electrical signal that constantly excites or drives the active elements in the transducer. The frequency of sound emitted by a continuous wave probe is equal to the frequency of the electrical signal. Okay, so here is our, let's just quickly draw a probe with, there's an element at this end, and wire comes through. By the way, a single element transducer may very well have one wire or perhaps two wires. One is a transmission wire, and then one receiving wire. So actually, let's do that. And actually, there's reality. These are the wires here. And actually, in reality, there's actually two elements in a continuous wave transducer, but we'll talk about that soon enough. So what they're saying is that whatever electrical frequency is put into the element is what the frequency. So if you're exciting the electrical wire at 5 megahertz, you will have a 5 megahertz wave produced. If it's 10 megahertz, a 10 megahertz wave is produced. So that is true. You are able to change the frequency by changing the by the frequency in the wires itself. There is, of course, every element has a happy place. And that's where it rings. That's where it wants to ring. So it's going to have a fundamental frequency. So pulse wave transducers. Pulse wave ultrasound system creates short duration electrical spikes that travel through the wire and strikes the PZT crystal in the transducer. This produces a process similar to just quickly striking the key of a piano. When the key is depressed, a small hammer. Okay, so really that page 123 doesn't tell us too much that we don't already know. And this is ugly anyway. Hopefully you guys saw that. Well, that's right. This is recorded. You just go back. So I'm going to go next to the next page, 124. How does the speed of sound in PZT affect frequency? Okay. In a pulse wave transducer, the speed of sound in lead zirconate titanate and the frequency of sound are directly related. Speed and frequency are directly related. The frequency of sound created by a pulse wave transducer is higher when the sound speed, when the speed is faster in the element, creates a higher frequency. When the speed is slower in the element, the frequency is lower. Speed of sound in most piezoelectric materials ranges from 4 to 6. Zoom in a little bit. C. Do I do CE? Yeah, let's do CE for C element. Speed of sound in the element is 4 to 6 millimeters per microsecond. That's considerably faster than the speed of sound in the body, isn't it? No, this value is occurring. This concept is illustrated. So, mathematically, let's just jump to page 125. We need to look at this mathematically, and then I can give you a illustration of what's going on. How does this thickness of piezoelectric material, lead zirconate titanate crystal affect frequency? So the thickness, PZT thickness and frequency are inversely related. Thinner active elements create pulses with higher frequencies. Okay, so thinner elements versus thicker elements. Now, this is we got to be sure what we're talking about with thinner and thicker. We're set up in this direction. I normally draw elements so that they're facing down, but that's not how we're doing it right now. So the thickness is there and there. All right, thin element, thick element. This guy is going to produce a wave about that. Damn. All right. Well, it's a very quiet wave. This guy is going to produce a wave more like that. So high frequency with a thin element, low frequency with a thicker element. Now, let's talk about the equation here. So frequency, I'm going to put FO, frequency operating there. Frequency, this is the happy place frequency for the element. It's where it wants to ring. It is the speed of sound in the element in millimeters per microseconds. Or your book says sound speed in PZT. So same thing. And then 2 times thickness. This is, guys, with just a little bit of changes, but really not that different. This is the same as frequency, megahertz. Well, I'll skip the megahertz part for now. Frequency is equal speed of sound over lambda. So we learned already that frequency is equal to speed of sound in soft tissue, for us, soft tissue, over the wave length. Remember, wave length. It's the same exact thing, and let me show you why. 2 times the thickness is wavelength. Let me show you. Now this time I'm going to draw my element the way I like to draw my elements. So now that's thickness. This is going to be the face of the element. Face of the element is also called an aperture, but I don't want to mess with that word right now. Okay, let's give myself a little more room to play with here. And what color should I'm going to still use the window? Okay, let's make this purple because it's pretty. Ooh. Rather than draw this again, over here, remember how I said the element is vibrating. When we hit it with an electrical charge, it vibrates. It goes kind of curves out. And then naturally, it's not going to stay out. It's going to curve. It's going to curve in. It's going to curve in, curve out, curve in, curve out. As it's vibrating, it gets thicker and then thinner. So the same thing is going to happen here. Every time when it gets hit with electricity, it's going to deform. That's a word I've been using. It's going to deform, which is another just way of saying vibrate. And so the sides are going to come in, and then they're going to go out and out. And this is going to be repeated until it stops vibrating. So what I figured out, and this is extra stuff. So you don't really need this, but is that every time it does that, it gets every time the crystal gets wider and thinner, wider and thinner. That's the same as compression against the air or against your skin, really. Compression, rarefaction, compression, rarefaction. And so we have a compression, rarefaction, compression, rarefaction, compression. And so what we end out having is the thickness the thickness of the element is 1/2 lambda. As I draw this, yeah, that's one. I'm sorry. Yeah, basically there's one cycle. This is 1/2, and then there's 1/2 of it that's left. That's already left the building here. That's the other half of that cycle. So half, 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 half. So that's why it's 2 times the thickness, because 2 times the thickness is lambda. And then at that point, we realize that we're dealing with the same exact equation that we already learned. Oh, and of course, the other thing to think about then is, let's just use our arrows like we've done before. If thickness, if this goes, thickness goes down, frequency goes up. If speed of sound goes up, frequency goes up. All right. Oh, awesome. I'm done with this chapter. We will talk about it more, but cool, we're done. I'm done, and I get to go have lunch, which is really awesome. I will see you guys on Monday. Hopefully you get to watch this either today or over the weekend. Adios, my friends.